The universe presents a profound cosmological paradox. While evidence suggests it is likely infinite, in extent extending without walls, borders, or edges, we are fundamentally restricted to a finite observable bubble. This is not a physical constraint, but a relativistic limit dictated by the interplay between the finite age of the universe and the expansion of the fabric of spacetime. To understand why one must distinguish between the age of the universe and the size of the observable region, the universe is approximately 13.8 billion years old. Naive geometry might suggest we can only see objects 13.8 billion light-years away. However, this assumes space is a static, rigid stage. In reality, the universe is governed by the Friedmann-Lemaitre-Robertson-Walker metric, meaning space itself is dynamic and expanding. As photons from distant galaxies travel toward us, the space they traverse stretches. Consequently, the source galaxies are carried further away while their light is still in transit. By the time these photons reach our detectors, the source galaxy is far beyond 13.8 billion light-years. It currently resides at a proper distance of roughly 46 billion light-years. This boundary is the particle horizon. It is not a physical wall, but a causal limit, the limit of light travel time in an expanding metric. Everything beyond this 46 billion light-year radius is fundamentally inaccessible, because the expansion rate of space is not uniform across time, governed by the density of matter, radiation, and dark energy. The distance light has traveled does not correspond linearly to the distance of the source. We are observing light emitted when the universe was in its infancy, yet that light has been subjected to billions of years of cosmic stretching redshift, which drastically alters our measurement of distance and energy. Furthermore, every observer in the cosmos occupies the center of their own unique observable sphere. This is an observer-centric geometric property, not a privileged position. Imagine yourself in an infinite dark warehouse with a flashlight. Your beam creates a circle of visibility, your observable universe that follows your every step. You never reach a wall, yet your view remains limited by the reach of your light. An observer on a galaxy, billions of light years away, occupies the center of a different overlapping sphere, seeing regions of space that are forever hidden from us. We are not at the center of existence, but we are at the center of our own causal reach. We live in a universe that is simultaneously boundless, offering no edge to reality, and bounded, trapped within the limits of light's journey through a stretching, expanding metric. Our observable universe is not a slice of the whole. It is a dynamic, shifting sample representing a negligible fraction of an infinity that we can never fully perceive, map, or interact with. The observable universe is not defined by a single wall, but by two fundamentally distinct boundaries, the particle horizon and the event horizon. These horizons serve as the definitive limits for both our observational past and our interactional future, yet they function in diametrically opposite ways. The particle horizon represents the limit of our past observations. It defines the farthest distance from which light emitted shortly after the Big Bang has had sufficient time to traverse the expanding fabric of space to reach Earth. Currently, this boundary sits approximately 46 billion light-years away in every direction. Crucially, this horizon is not static. It is a boundary of history. As the universe ages, light from increasingly distant regions completes its journey and finally enters our observable sphere, causing the particle horizon to expand outward, constantly revealing new cosmic territory. In stark contrast, the event horizon represents the limit of our future reach. It is situated much closer at roughly 16 billion light-years away. This boundary demarcates the regions we can observe from the regions we can meaningfully influence. Any galaxy situated beyond this threshold is causally disconnected from us. If we were to send a light-speed signal toward such a galaxy today, the expansion of space would carry the target away faster than our signal could close the gap, meaning the message would never arrive. This creates a profound asymmetry. We can observe galaxies that we can never contact. These galaxies exist within our observable universe, but they reside permanently outside our reachable universe. Furthermore, due to the influence of dark energy, which drives the accelerated expansion of space, the event horizon does not expand. It contracts. With every passing moment, more cosmic regions slip beyond this boundary, becoming unreachable. We are essentially witnessing the cosmic neighborhood empty out in real time as galaxies cross into an unreachable realm while their final ancient photons continue to drift toward us before inevitably fading into redshifted invisibility. To understand the universe, we must first discard the popular but misleading image of galaxies flying through a static, empty void, like bullets fired from a gun. This misconception fundamentally misrepresents the nature of the cosmos. In reality, galaxies are mostly stationary, relative to their local neighborhoods, bound by gravity in clusters and superclusters. The phenomenon we observe, the recession of distant galaxies, is not caused by motion through space, but by the expansion of space itself. Consider a loaf of bread dough with raisins mixed throughout. As the dough rises, the raisins move apart from one another, but each individual raisin remains stationary relative to the dough immediately surrounding it. The universe behaves exactly like this, except the dough is the fabric of spacetime itself. This expansion is not occurring at a single point. It has no center and no edge. Instead, every point in space expands equally and simultaneously, stretching the fabric uniformly in all directions. Because the universe is all there is, space does not expand into anything. There is no outside container. This uniform expansion leads to a direct mathematical relationship. The farther away an object sits, the faster it appears to recede. If a galaxy 1 million light-years away drifts from us at a specific velocity, a galaxy 2 million light-years away drifts at double that velocity. This relationship holds across the observable universe because expansion is cumulative. We are measuring the sum of all the small expansions occurring in every segment of space between us and the distant object. Push this pattern to its extreme, and we encounter a profound violation of intuition galaxies that recede faster than the speed of light. Beyond a certain distance, currently measured at about 14 billion light-years, galaxies recede from us at speeds exceeding light. However, this does not violate the laws of physics, specifically special relativity. The cosmic speed limit applies only to motion through space. In contrast, the expansion of the universe involves space itself stretching, and this growth has no theoretical speed limit. Because the fabric of space-time can stretch as fast as conditions allow, distant galaxies can recede at any velocity, even multiples of the speed of light, while remaining stationary in their local reference frames. This leads to the bizarre reality of light fighting against an expanding river of space. Photons from these ultra-distant galaxies travel toward Earth at the maximum velocity allowed by nature, but they are being carried backward by the expansion of space faster than they can advance forward. In the early universe, when expansion was slower, these photons could make forward progress and eventually reach us. But today, photons emitted from those same distant galaxies are trapped. They will drift away from us forever, despite traveling at light speed toward our telescopes. To understand the absolute limit of electromagnetic observation, we must travel back to when the universe was only 380,000 years old. Before this pivotal moment, the cosmos was a roaring, homogeneous furnace of ionized plasma. Matter was too hot, exceeding roughly 5,000 degrees Celsius to allow for the formation of stable neutral atoms. Consequently, protons and electrons drifted as a roiling soup of free charged particles. In this state, the universe was fundamentally opaque. Photons, the carriers of electromagnetic radiation, could not travel in straight lines. They were constantly scattered by the dense swarms of free electrons. Think of this as being trapped inside a wall of solid metal or a thick, impenetrable fog where every photon hits a particle and bounces off in a random direction like a pinball. Light was locked in a state of thermal equilibrium with matter, effectively trapped and unable to carry any information across cosmic distances. This state of opacity ended abruptly due to cosmic expansion. As the universe expanded, it cooled. Once the temperature dropped below the critical threshold of roughly 5,000 degrees Celsius, a process called recombination occurred. Electrons finally slowed down enough to be captured by atomic nuclei, forming stable neutral atoms of hydrogen and helium. This had a profound consequence. With the free electrons gone, the fog cleared. The universe became transparent almost simultaneously across its entire volume. The light that had been scattered and trapped for 380,000 years was suddenly liberated. It streamed outward in every direction, carrying the thermal signature of the universe at that specific moment. This ancient light is what we detect today as the cosmic microwave background, CMB. It fills the sky as a faint glow of radiation representing the surface of last scattering. The spherical shell marking the moment photons last interacted with matter before embarking on their long journey to our detectors. However, this shell acts as a fundamental barrier to our observation. It is an absolute impenetrable curtain. Because the universe was opaque prior to this release of light, no electromagnetic telescope, regardless of its sensitivity or technological sophistication, can pierce this curtain to observe the first 380,000 years of cosmic history. Everything that occurred before this epoch is hidden behind a wall of scattered plasma. While we can extract extraordinary detail from the CMB, such as the tiny temperature fluctuations that seeded the future structure of galaxies, we are effectively blinded to the truly primordial universe using light. To investigate what happened during the first second after the Big Bang, we cannot rely on electromagnetic radiation. We must turn to alternative messengers, such as primordial gravitational waves and neutrinos, that can pass through the plasma curtain unimpeded. Until then, the cosmic microwave background remains the practical, definitive edge of our observational reality, a faint ancient fire marking the absolute limit of what light can reveal. We currently inhabit a rare, golden age of cosmology, a brief window of time where the universe reveals its history with startling clarity. However, this window is closing. Roughly 5 billion years ago, the dynamics of the cosmos shifted irrevocably. While the gravity of matter initially acted to break the expansion of the universe, a mysterious component known as dark energy began to dominate the cosmic inventory. Today, dark energy constitutes approximately 68% of the total energy density of the universe, and its behavior fundamentally defies our intuitive grasp of how energy should work. Unlike matter or radiation, which dilute as space expands, dark energy maintains a constant density. As the universe grows, more space is created, and with it, more dark energy is added to the system. This creates a runaway feedback loop. More space means more dark energy, which in turn drives the expansion to accelerate even faster. This acceleration is the defining force of our future, fundamentally altering the relationship between observers and the cosmos. This accelerated expansion creates a dramatic, tragic divergence between our two horizons. While the particle horizon, the boundary of what we can see from the past, continues to expand, revealing older light from increasingly distant regions, our event horizon, the boundary of what we can ever reach, has begun to contract. Currently sitting at about 16 billion light-years, this event horizon will asymptotically approach a fixed distance of approximately 17.6 billion light-years. Galaxies situated beyond this limit are crossing a point of no return. Even if we were to send a signal at the speed of light today, the space between us would expand so rapidly that the signal would never arrive. Consequently, the observable universe is beginning to empty out. Every single day, thousands of galaxies cross this event horizon and slip into unreachable territory. We may continue to see their ancient redshifted light for billions of years, but this light is a delayed broadcast of their past. Their present and future evolution are now permanently severed from ours. Over the next 100 billion years, this process will accelerate until only galaxies bound together by local gravity, our own local group, remain visible. This leads to a chilling prospect for future civilizations. Astronomers emerging billions of years from now will inhabit a profoundly lonelier cosmos. Because dark energy will have stretched the light from distant galaxies into undetectable long wavelength radio waves, the cosmic microwave background will vanish from their instruments. These future observers will look into the night sky and see nothing beyond their own gravitationally bound cluster. Lacking evidence of cosmic expansion, the Big Bang, or the larger galactic web, they might scientifically conclude that they live in a static eternal universe containing only their local islands of stars, surrounded by an infinite empty void. They would be fundamentally wrong, yet they would have no way of discovering this truth, as all contradicting evidence would have drifted beyond their event horizon, forever inaccessible. We exist at the unique intersection of cosmic history, where the evidence is still present, before the universe isolates itself into an era of profound, observational darkness. To resolve the fate of our universe, we must look to its shape. Space can curve in three distinct ways, each dictating a different destiny for existence. If the universe curved like a sphere, positive curvature, parallel lines would eventually meet, and space would be finite in volume, destined to collapse back into a singularity. If it curved like a saddle, negative curvature, space would diverge, infinitely expanding forever, as matter dilutes into cold emptiness. Observations of the cosmic microwave background, CMB galaxy clustering, and distant supernovae all converge on a startling result. The universe is flat to within a measurement error of 0.4%. This flatness creates a critical density puzzle. For space to remain perfectly flat, the universe must contain an exact amount of matter and energy, roughly equivalent to 6 hydrogen atoms per cubic meter. This is an impossibly precise balance. If the density were even slightly higher or lower in the early universe, expansion would have amplified that curvature rapidly over billions of years, making the current universe either collapse or fly apart too quickly to form galaxies. The fact that we sit right on this knife edge suggests either an incredible coincidence or an underlying physical mechanism. Cosmic inflation provides this mechanism. It proposes that during the first fraction of a second, between 10 to the power of minus 35 and 10 to the power of minus 32 seconds after the Big Bang, the universe underwent a brief exponential expansion. Space grew by a factor of at least 10 to the 26th power, an effect akin to blowing up a wrinkled balloon so large that the surface appears perfectly flat to any observer sitting on it. Inflation smoothed out any initial curvature, forced the universe toward flatness, and created the uniform conditions we observe today in the CMB. However, this leads to a disturbing implication. If inflation drove the universe to flatness by stretching it enormously, the total cosmos must be vastly larger than our observable bubble, likely infinite. In an infinite universe, quantum mechanics mandates that every possible configuration of matter must eventually repeat. This means that somewhere in the vastness of space, there exists an identical copy of our observable universe, complete with an exact duplicate of Earth, and an identical version of you reading these words. In infinite space, every choice you could have made, every alternate path your life could have taken, actually occurs in some distant, physically identical region. Finally, we must consider topology, the shape of space. Even if space is flat, it could be finite if it wraps around itself like a video game screen. Scientists have hypothesized the universe might be a three-torus, a structure that connects opposite edges, essentially making it a giant three-dimensional donut. While current observations have ruled out small loops that would create visible repeating galaxy patterns, they cannot eliminate a topology that operates on a scale larger than our observable horizon. If the universe is a giant flat torus, it would be finite in volume, yet have no edge or center, and we would remain forever unable to detect this global structure. Thus, the universe sits at the intersection of these grand questions. Is space infinite housing, infinite copies of our existence? Or is it a giant finite loop that hides its true shape beyond our reach? For now, the simplest explanation, an infinite flat cosmos, remains the generic prediction of inflationary cosmology, leaving us as one possibility among infinite variations stretching endlessly into a darkness we can never fully map.